For our BME ECE462 final project, we did a heart rate monitor with feedback system. Exercising is essential to maintaining a good health, and one way to do this is to measure the heart rate because that is a good example of the exertion level of the athlete at that time. Current machines use a more passive approach to monitoring heart rate, such as you have to hold the metal handles in order to get the heart rate, and this unfortunately isn't a continuous feedback. If you let go, you'll no longer get your heart rate, and it is often awkward to try to exercise while holding the handles. Our solution would be to continuously measure the heart rate and provide feedback with auditory and visual elements. The user would define their target heart rate, and with the minimum and maximum, we would use the software to see if they were above, below, or in the maximum heart rate. And our prototype will be a standalone unit, but the future will be defined later in this presentation. For many reasons, our project would be a good implementation of a heart rate monitoring system. For the convenience and comfort of the athlete, they would not have to continuously hold the metal handles. The ECG leads would be connected to their body, and the heart rate monitoring system would allow them to do more complicated training workouts. Research has shown that having the system to provide feedback would be a good approach to increasing intensity and workout time of the athlete, and for medical reasons, many people can't go above a certain heart rate without having medical risks, so this would be a good alternative for them to be able to exercise while not having to worry about going above that said heart rate.
So our project is going to have the following approach. Earlier in the semester, we set up a Arduino-based ECG system, and that was done by creating a PCB that was essentially an Arduino shield or something that plugs directly into an Arduino microcontroller, and then it spoke with LabVIEW to provide some beats per minute information about the heart rate. Really what we're going to do in this project is we're going to take that core and we're going to kind of expand upon it. We're going to add some additional LabVIEW code where LabVIEW then sends information back to the Arduino. Then the Arduino will drive some hardware feedback that the user will be able to experience in the middle of their workout. So we have three major sections. The first is going to be LabVIEW software. So we added a couple different things. First off, we wanted to make sure that the user could input their target heart rate, and that's done, as you can see on the right side. You set a minimum and maximum. Just like before, the LabVIEW software is going to be constantly monitoring the beats per minute of the subject, and as the BPM changes zones, and we've defined zones as above target, in range, or below target, the LabVIEW is essentially going to send a little flag back to the Arduino by doing a serial write, and we'll talk about that more once we get into the Arduino code section. In addition, we have a couple of software buttons that are going to control the feedback. We have a feedback on-off button, and we have volume up and volume down for the speaker. And as you can see on the right there, we've also put in some software LEDs that mirror what you are actually going to see inside of the hardware. So what we did was we put together a breadboard that has all of our hardware feedback. The first circuit is going to be 3 LEDs, pretty simple circuit. Essentially it's being driven by Arduino digital outputs at 5 volts, and depending on what zone you're in, a different LED is going to light up. The Arduino output pins are going to drive through a resistor, through an LED to ground, and as you can see in the picture over there, the blue light is illuminated. That is what in range is going to look like for our user. Next, we have a speaker circuit. Pretty similar implementation. We have a digital output pin from the Arduino that is going to be driving the base of a BJT. That's going to cause collector current to flow from the rail to ground through our speaker, and it's going to essentially make our speaker start sounding at a rate of, what is it? I think it's 490 hertz. So the Arduino software, basically it's piggybacking off of the original ECG code. It's going to read the incoming serial command from LabVIEW, like I was saying a second ago, and basically it's going to take that command and it's going to pull out a number, and depending on what number it receives, it's going to take a different action. Some of those actions might be driving a particular LED, depending on which zone you're in. It could be turning on the PWM, or which is essentially driving that speaker. It could be raising or lowering the volume, which is changing the PWM duty cycle, or it could be just completely turning on and off the hardware board. So some of the struggles we noticed, or hurdles I suppose, while we were going through and making this project, serial write inside of LabVIEW actually causes a software delay of about 3 seconds or so. And something that's doing is it's affecting the beats per minute calculation. It's forcing it to be a low number because of this delay. So that's something we tried to kind of combat by creating a little bit of digital logic inside of LabVIEW. Originally, we were just continuously sending information back towards the Arduino board with that serial write, but we wanted to put some logic in there so that it would send the absolute minimum amount of data possible. So essentially, it's going to send one packet of information whenever it has to, and then it won't send any more after that to basically cause these delays to go away. Minimize the issue, but it didn't completely eliminate it. We'll talk about that in a second.
For our results, we tested the device on a subject, but unfortunately, even with moving the ECG leads to the chest, there was way too much movement, which caused the BPM to be off from the actual heart rate. And to compensate for this, we used a signal generator with a heart rate signal to test our software. We used the signal generator to have a example heart rate that went up and down through all the transitions, and it showed the correct hardware and software feedback from that. Unfortunately, with the speaker that we had, the speaker volume changes could not be noticeable, but we could read that the PWM signal duty cycle was actually changing by viewing it on the signal reader. You will see a video demonstration of the device after this presentation is done. For the future of this project, we would want the device to be built into the exercise equipment at a gym. There would be additional software and many changes that we would need to make to the device, but it could be a very positive aspect, such as if we want to put it into a machine, we would be able to eliminate the need for 2 different devices. We would be able to put it on one that would do all of the data analysis and analyzing and sending out the feedback in one, so we wouldn't have that delay that we had before, and it would only need one microcomputer. For additional hardware, we would need a better way to read the heart rate that would not have as much noise, and we would also be able to put more development into the feedback, such as having vibration and different kinds of feedback like graphs with more data that the users could see.
In addition, research needs to be done into the psychology and some of the human factors behind our implementation. Truly, the only way to solve the problem is, as we described with current workout equipment, is to make sure that whatever solution comes up, whether it's ours or a competitor's, is as accessible to people as possible. Further research needs to be done into what sorts of design decisions can be made to make sure that anybody walking through the gym can walk up to a solution and really use it to make a positive impact on their health.
This is the test setup we were using for our on-athlete testing. Over here on the left side, you can see the Arduino-based ECG that we created earlier in this semester, previously tested, and really we're just using it in a kind of a new function here by adding a secondary breadboard with a couple of circuits on it. First off, right down here, this is a view of the circuit that we'll be detailing a little bit earlier inside of this video that's hooked up over onto a speaker. And then up here, this is a series of 3 LEDs. The one that's currently on right now is representative of a heart rate that is higher than the athlete's selected range. Blue is going to be, if the heart rate is inside of the selected range, and then the bottom LED that is currently extinguished is going to be if the athlete is currently below the selected range. This is going to be our LabVIEW front panel, and as you can see up in this section here, we have a couple of separate buttons that are all really useful for this project. First off, we have a minimum and maximum heart rate. Those are the thresholds that an athlete would select depending on what they want their target HR to be. We have feedback on, and that's what turns on and off all of the lights and sounds over on the board. We have volume up and down. That's going to change the PWM signal that drives the speaker. And then we have some software buttons over here that can basically show exactly what the LEDs are showing over on the actual board itself.
Here can be seen the type of noise that can be on the ECG lead if there's a lot of movement. Right now the athlete is not trying to stay still, and the signal has a lot of motion artifact noise from it, and no BPM can be clearly read.
On an earlier portion of our video, whenever we have the ECG hooked up to an actual athlete and it's moving on a treadmill, the noise actually ends up being a major issue that messes up our BPM calculation, and therefore the rest of the circuitry doesn't really want to go along with it. So what we're doing in this case is we're actually going to be simulating a ECG signal by using one of these signal gens up here that's hooked directly into our Arduino board. And we will show you the effects of raising and lowering the BPM compared to what the established threshold is. So right now, as you saw in our LabVIEW section, our minimum heart rate is set for 60 BPM, and we're running at about 70 by using this signal generator. What we're going to do is we're going to switch, or we're basically going to turn down that beats per minute by, adjusting the arbitrary waveform generator. And as we fall below that 60 threshold, you'll see our board react. Inside of LabVIEW, we've set our upper BPM threshold to be 90 beats per minute. Right now we're running at right around 80 beats per minute. We're going to go ahead and raise the BPM, and you'll see the circuit react. So as we cross through that threshold, the upper LED ends up going on, and the speaker gives us kind of like a 2-pulse tone, which is just as we programmed in the Arduino. You're also noticing one of the side effects that we're going to be mentioning inside of our paper. Sometimes what ends up happening is when you cross one of the thresholds, basically LabVIEW sends kind of a little bit of information over to the Arduino, and there's a delay in that send process. It kind of keeps LabVIEW all tied up, and because of that, it ends up calculating the beats per minute wrong. So sometimes when you cross from boundary to boundary, there's a little bit of a fluctuation right around that boundary, and then it ends up stabilizing a couple of seconds later.